Uh, okay, so the idea for today is just to continue talking about the random variables. Again, like the random variables are just a particular name that you can give to a function that depends on the outcomes of your experiment. So I guess like we could just start continuing talking about certain specific random variables. So just to give you a reminder of the two that we saw last time, right? So the first one was the Bernoulli random variable. That's kind of like the most basic random variable. It's kind of the idea is like it's what would represent like an experiment where the outcome is either yes or no, or it's basically a binary outcome, right? So it's either yes or no, zero or one or zero, or like heads or tails, right? So all of those experiments that have only two outcomes are kind of fall into the category of a Bernoulli random variable. You call them parameter P because the idea is that now you're allowing for the possibility that both outcomes have different probabilities. So yeah, so this one was the most basic random variable. And then the one that after the Bernoulli random variable is like the binomial random variable. So essentially, the way this one works is that you do a Bernoulli experiment n times, okay? And here you are interested in counting how many successes you have in these n experiments. And again, successes here can mean that you got a certain number of heads, or that if you're working with like a computer code, that in your code you have like a certain number of ones. So anything that kind of has like again two possible outcomes, but now you're repeating them over and over, that call enters into the binomial random variable, as long as these experiments are independent of one another. So that's kind of important. Otherwise, like the probabilities that we computed last time, if you remember them, you wouldn't be able to just multiply the probabilities to of like the different outcomes. So okay, so that's kind of what I was saying on Monday, and then I computed the expected value of these random variables just to give you like an idea of how they work in general. So the next random variable, and again, I'm not necessarily expecting you to memorize these because there are a bunch. Like what I'll probably do is give you the formulas, but I would expect you to recognize which random variable corresponds to which formulas. So I would give you, I'm probably will just end up giving you something like this formula, but I wouldn't tell you what this represents, right? So you would have to remember that that's like the binomial one, for example, or something like that. But yeah, like memorizing all these formulas, I think can be a bit too much. So here's another one, which is kind of fun. Well, maybe I should ask first, like, are there any questions so far? Is everyone good with this? So let me just give you a few more random variables before we do other things with random variables. So a few other random variables. So the first one is that we can also study. It's called the geometric random variable with parameter P. And here, the idea is like you are going to do, you are doing like some independent Bernoulli experiments. So you're performing independent Bernoulli experiments. Okay, and with a parameter P, and you will continue until you get a success. You will continue the experiments until you get a success. Okay, so what do I mean by this? Like, again, you could imagine like you're throwing a coin, and a success for you means getting a heads. So in these like in this random variable, the random variable, or in the experiment that we're doing, the first moment you get a heads, you would stop throwing the coin. So it's kind of like an experiment where there's no fixed number of repetitions you're doing. You just stop the moment you win for the first time. Okay. So here it could mean like, yeah, like in our examples that we have been doing, it's the moment. So in our examples, it's like kind of like the moment you get heads, you stop. Or if again, like you could imagine that you're writing a code in binary. And so the moment success would be like typing a 1. So you can imagine you're right, just typing them, you're typing the code at random. Like you have like your fingers like on those 2-digit 0-1, and you're typing at random. And the moment you a 1, you kind of stopped typing. So it would be also, so it could also be like the first time you get a 1, you get a 1 on a binary code. You stop, etc. So anything, it is kind of like you cannot again, but you just stop the moment you got what you wanted. So X is just going to count the number of experiments needed to get a success. So here is our random variable here in this setup. X is going to represent the number of experiments you need in order to get a success. To get a success. Okay, so yeah, that could be an interesting question. Just give me a second. Sorry about that. Could be. Okay. Okay, so I see. So the question is, how many experiments do you have to do to get a success? Well, maybe you're lucky and you got heads the first time, right? So you could, at least you need to do it once in order to win, right? So X at least has to be greater or equal to 1, right? But the question is then, how many times will you need to wait until you get a win? Well, maybe, like, again, if you think about getting heads, like maybe you waited 3 times, you have to throw it 3 times or maybe 10 times, or maybe actually you have to throw, like, there's nothing like really against the idea that you could always get tails for a long period of time before getting heads. Of course, you would think that is very unlikely, but it's not an impossibility. So actually the values for X are going from 1 to infinity. Is that making sense? Because you may have to wait like an eternity to get a win. I mean, we wouldn't expect that to happen that often, of course, but it is a possibility, right? So the number of experiments needed may just go from 1 to infinity. Is that okay? Is that clear? So so we cannot like decide ahead of time like how many experiments it would take, but the idea is that once you tell me what you can say is like, what's the probability that you will get a win in the 3rd attempt, or what's the probability that you will get a win in the 5th attempt? So you can give the probabilities for like a specific number of experiments performed. So that's kind of like this is what we're going to compute right now. So if you write something like this, let me see what the name. Oh, yeah, something like this. This would be the probability that on the nth experiment, you get a win. A success, but not before. Okay. So the question is, what would so basically it's kind of like saying you got heads until, sorry, you got tails until the nth time, and on the nth time you got a heads, right? So what's the probability for that to occur? What do you think it would be? It's kind of like maybe I should do it more diagrammatically. I don't know if this is too confusing. What I'm saying is that you have like a sequence of outcomes. So outcomes, and you have a failure. Let's call it failure and success. You have failure, until the nth time, and on the nth time you have a success. So I'm asking for the probability of getting this sequence, right? Of failure until you get to the nth time. I don't know if that makes it more clear. What's the probability of having this specific sequence of outcomes? Yeah, good. Okay, right. So you can write like the probability of each individual event on the top. So 1 minus p is failure, 1 minus p is failure, 1 minus p is failure, blah, 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 until you get to p, which is the only one, which is success, right? So because the events are independent, that's the assumption again, the probability just multiply. So you get, yeah, correct. You get 1 minus p to the n minus 1, because you got n minus 1 failures times p. or q to the n minus 1 times p, if you remember that q was 1 minus p. Is that making sense? And is that okay with everyone? And then, I mean, there's two things you could check because that will be also useful later on. Like, first, like you could ask, I mean, there are like, I'm telling you the probabilities for, you know, for each of these possibilities, right? Like for like getting a success on the nth trial or getting a success on the n+1 trial, I mean, on the 10th trial or like the 20th trial. So one question that you could ask is, what is the value of all this? If you add up all the probabilities, right? What should you get? So let's just work it out. So what does that mean? It means like the probability of getting a success at some point, right? Because here, if you let n go from 1 to infinity, it's kind of like saying, well, now I'm not specifying at what time you want. I'm just saying like, I just want to know if whether I win eventually, right? And so let's try just check what this probability should be. You get this, and this is p times the sum of n equals infinity of q to the n minus 1. Okay, and now anyone remembers what sort of series is this?
Just a geometric series.
Correct. And what's the value for this series?
So I think if Q is between -1 and 1, it should converge.
Correct. Yeah, which is useful because we're working with probability, so that's good. The convergence is never a problem, more or less, in these problems with probabilities. So what was the value for the geometric series?
It's a 1 over 1 minus r, I think, if you start the index at 0.
Right. Okay. Yeah. So we can do this trick of reindexing the series. I don't know if you remember this trick. Like you could like just call this like you can call this m. You could call m like n minus 1. It's like a change of variables, right? So this becomes like the series from m equals 0, right, to infinity of q to the m. Is that making sense? Like I imagine like, I'm not sure if everyone has to take differential equations but I mean, this is a trick very common if you take Math 244 or probably Calc 2, right? Like you have to reindex like this series from time to time. And yeah, here, for like, if you started a series of 0, it's 1 over 1 minus q. But 1 minus q is p, so it's 1 over p, so it's 1. So kind of what this is saying is that, yeah, if you do infinitely many experiments, you will win at some point, right? Because with probability 1, you get a success, which is kind of reasonable. So if you wait an infinite amount of time, in a sense, you will eventually see a success. If you do this infinitely often, if you do the experiment infinitely often, you will win eventually, at least once. Eventually, you'll get a success. Is that making sense? I mean, that's kind of reasonable, I suppose. Like, of course, it's not too practical. No one would in practice will ever be able to like do an experiment infinitely many times. So it's not like a verifiable statement in that sense, but it's like plausible given what you. Otherwise, what would it mean to say that a probability, like an outcome, has a positive probability if that doesn't mean it wouldn't occur at least once if you do it infinitely many times? Like, it's not clear how could that even be true. And then is that okay? So, and then the other one you could the other thing you could check playing with geometric series. I mean, it's just fun to. I won't do this for every single one, but it's kind of fun to do it at the beginning, especially just to remind you what sort of skills from Calc 2 you may need to remember. You could also find the average value of this random variable. So if you remember the definition, it would be the series from n equals 1 to infinity of n times the probability that x equals n. Okay. Because those are the values that the random variable is taken. And so what is that equal to is the series from n equals 1 to infinity. What is the probability that x equals n? We wrote it, right? It was p times q to the n minus 1. Okay, could this, let's see if this one works still with the trick from last time. That's not how I was planning on doing it, but I suppose it could work. Let's see, I mean, now I'm doing it out of pure speculation. Okay, anyone remembers the trick that I did last time? I haven't tried it this way, so I hope I don't do something stupid. But it's speculative. Yeah. What was it? It was to write it as a derivative, right? Is that okay? Everyone okay with everyone with me? So let's see. And then this one starts at n equals 1. And so what? This is a power series can be differentiated term by term, right? That's one of the theorems of power series. So that doesn't seem I'm doing anything too stupid here. And then, but since now this one starts at 1, right? This gives you what? Q over 1 minus Q. Is that the derivative in this case? Because it started at 1, right? So that should be, I think that should be correct. Yeah, is that making sense? Yeah, and then if you take this, you can find this derivative using the quotient rule, and you get 1 minus Q squared. Good. But 1 is 1 minus Q is P squared, so you get P over 1 over P squared, and then this is 1 over P. Is that okay? So the expected value here is 1 over P. Sorry, the average value is 1 over P, right? Oh, the expected value, those are synonyms. Is that reasonable? Is that making sense? And so what does that mean? Like, for example, for a third coin, right? Let's make this more concrete. So for a third coin, where the probability is 1/2, then that means that the expected value is 1 over 1/2, right? Which is 2. So that means that on average, if you throw a third coin, then you would, on average, then you would expect at least like that you need 2 successes to get a heads, which is more or less plausible. But of course, when you say here on average, you have to imagine that it is like a huge average, right? Like done over like millions of millions of millions of millions of millions of experiments, right? For this to be approximately true. So, but that's kind of like the interpretation. So it is like a plausible interpretation of what you would like to say. Does that make sense?
So just to reiterate, I guess the expected value, you can interpret it that if you do 2 like throws, then you're going to get heads like once. I mean, obviously it's not, that's kind of
right. Yeah, like what this is saying is like, imagine you could assemble hundreds of millions of people in a row, a straight row, like each one throwing like a coin, like you know 2 times, like so the overwhelming majority of those people would have had like at least a heads in those 2 success, two attempts or something of that sort. I mean, which is kind of like kind of plausible given what you mean, saying that the throw is fair, because like you would expect that on it should, of course it's just like in practice it's like if you throw like a coin 3 times and you get 3 times tails, it's not that it's not impossible. Of course that would happen. So this is why you have to be careful with this like interpretations of averages and expected values, right? Because you may never just like in practice, like it really means like imagine that you would do this over and over and over and over and over and over and over. And so it's not that it doesn't. So if you don't happen to run into that value for successes, it's not that there's anything wrong with your coin or the experiment. So yeah, it is. It just requires a little. So it's a subtle point, but I mean, it's kind of still plausible if you kind of imagine like this is done like almost like infinitely many times. Like that's kind of what you would really need in practice for this to be 100% true, But of course, you cannot do it that way. Because like the series, like went to goes up to infinity, right? So. Is that okay? Is that making sense? So yeah, so that's cute. That's nice. Okay. Then the other one, again, I don't want to bombard you with tons of different random variables. The book has a lot. I'm just trying to give you like kind of like which are like the most common that appear. But again, I'm not expecting you to memorize all of them in a sense, because like there's just so many. So I'll probably just give you the formulas, but I would expect you to recognize them. So the next one is the one that's called negative binomial random variable. Of parameters or P. So it is similar to the one that we just did. So it's similar. So let's see. You're doing Bernoulli experiments. You're doing independent Bernoulli experiments. And you will continue until you get R successes.
So is this like the same as the geometric thing?
Oh, okay, right. Here's the difference. Like this is right, or rather, it's like it is like a generalization of this one, right? Like of the geometric one. Because in the geometric one, you just stop at the first success, right? In this one, you just continue until our success. So it's like,
yeah,
right. So it's like the geometric one is like a special case of this one when r equals 1, right? So yeah, that's kind of what the remark that I was going to make. So the geometric random variable is a special case of this one. Special case of this one with r equals 1. So again, it's kind of like if you you kind of pick your favorite interpretation. So if you think about coins, it's kind of like you keep going until you get r successes. If you think about digits on a code in binary, you kind of keep typing your code in zeros ones until you get r ones. Okay, so it's kind of like it's more or less the same, but you just keep repeating it. So it's so again, how many successes do you have to wait for? Like it could go from, okay, now it has to start, I suppose it has to start at r, because you cannot have like, you know, x has to be at least greater, maybe I should say what x is, right? So x is going to be the number of experiments you have to wait for, right? Experiments you perform until you get r successes. So of course now x has to be at least greater or equal to r, because like how could otherwise you could get r successes. So x has to be at least greater or equal to r, and it could be, I mean, you may have to wait like an eternity, right? So it could go to infinity. But everything else is kind of the same like as what we had before. And the names are very suggestive. So the probability that you had to do n successes and experiments, right? What would it be? Well, it requires r successes. So there should be a p to the r. Then it requires n minus r failures, right? So there should be a q to the n minus r. And then now the only difference is that you're allowed to permute, like, you know, where the failures and the successes happen. The only restriction is that the last experiment that you did have to be the last success. Otherwise, you would have stopped earlier. So you really have n minus 1, you know, outcomes you can shuffle. So it's kind of like one of these n minus 1 chooses r minus 1 combinatorial formula. You cannot put n again because you're fixing the last one to be a success, right? Because if the last one were not a success, it would have stopped earlier. So that's why it has to be n minus 1, right? Because the last one is fixed to be, last one must be a success. Is that making sense? Okay, and then and again, like you could kind of like the book, I believe, computes like this expected value. Like I think it's somewhere in here. Let me see. I think it's just like yeah, it should be r over p, which kind of makes sense. And you can check it. I mean, you can check it like the way the book does it. I mean, or you could try to see if you can play with it with the trick of introducing derivatives. That one should also work. But you know, like going over this derivation again is kind of like always the same thing. So yeah, you just check the book or try doing it, like try manipulating it with with the derivatives trick. You may need I think you may need a partial derivative in this one, like the one that we did last time, because it's like with the binomial one. but check the way that the way the book does it, or by mimicking the partial derivative trick from last time. But yeah, either way, you should get to it. But it kind of makes sense, like, you know, it's because this is like R times 1 over P, right? So it's just like saying like, well, if you have to wait 1 over P on average to get one success, if you want R successes, since everything is independent, it's kind of just, you know, kind of starting from 0 again, right? So you just wait another 1 over P for the next success and another 1 over P for the next success. So if you think about it in those like more like plausibility way, it is like reasonable. Is that okay? So yeah, I think, okay, which ones have I told you? I have told you like the Bernoulli, the binomial, the geometric, and this negative binomial. So I think that kind of for now that's good enough. The one that I want to do next is a Poisson random variable, okay, which is an interesting limiting case of the binomial one. So let's see. Yeah, let's take a 5-minute break, and once we come back, I'll do the Poisson random variable, if that's okay. It's just like maybe better to do a fresh start because it will be derived in a slightly different way. It's a cool derivation, but it's better to just look at it from with a new perspective. So yeah, once we come back, I'll tell you how to do this other random variable. Okay, now let's go to this other one, which is a Poisson random variable. Okay, so how can you get this one? This is an interesting one. Yeah, this is one of the important ones. So we'll discuss this one multiple times throughout the remaining part of the course. So the idea here is that let's start with the Bernoulli random variable. So we start with Bernoulli random variable. Sorry, the binomial random variable. With parameters and P. So again, that was like the number of successes in N trials. And this one was given by the probability that X equals I equals N chooses I times P to the I 1 minus P to the N minus I. Okay, and now in the Poisson, like now we're kind of going to take a limit of this distribution. Okay, so we want to take a limit as N goes to infinity. So you want to make the number of trials very, very, very large. Okay. The problem with just doing that is that you won't get like a very interesting limit on its own. I mean, it's kind of a bit ill-defined because you know, if you thought about n going to infinity, right, so what would happen as n goes to infinity here? What would you get? This is a number between 0 and 1, right? So if you multiply a number between 0 and 1 with itself many times, goes to infinity, that should go to 0. So this kind of looks like a 0. And then, well, then you have to look at this combination, n chooses I symbol. What happens as n goes to infinity? Like, you just have to, you know, what, like, so as n goes to infinity, this would be like, in fact, I'll need the expression in a moment. X equals I is another way to write it is n factorial divided by I factorial, n minus I factorial, times p to the I, 1 minus p to the n minus I. So I'm just saying, if you just take n going to infinity, this goes to 0. This would be a constant, right? So this remains what it is. And what happens with as n goes to infinity here, if you are fixing p and I? Well, the problem is that once n is really large, then there won't be almost no difference between n factorial and n minus I. So it's kind of, this is going to go basically to 1. So you're getting 1 times 0. So you're kind of getting like in the limit, you would be getting 0 as a probability. And that's kind of a bit too much of a very bad approximation. So so just taking n go to infinity is not like a very useful thing to do on its own. So this would be like going to 0, going to 1. So not a very interesting limit. Is that making sense? So that's not like the best idea, but what you can make to modify this is what you can do is like kind of as you're taking n going to infinity, you're also imagining that p goes to 0. So as n, so that the fix of this, the fix is to, as n goes to infinity, take p going to 0 as well. Of course, like now this is going to sound, that sounds a little bit weird. I have to say what I mean by that. But and just if you thought about the formulas, what could make that a bit more, sorry, yeah, p going to 0. At least what could make that more slightly more interesting is that then 1 minus p, that would go, that should be kind of like 1 if p is going to 0. So you get like 1 to the infinity. And I don't know if you remember, 1 to the infinity is kind of one of like these indeterminate forms in L'Hopital's theorem for finding limits. So that can give you like a chance of finding something useful if you just kind of take the limit in a smart way. So the way to take the limit in a smart way is just to say that you're going to take the problem around is that you have kind of two variables, p and n, if you want to take the limit that way. So what you kind of do is take the limit in such a way that the ratio between them remains fixed. So you take the limit in such a way that p over n, or p times n, yeah, p times n remains a constant. Okay, because p is kind of going to 0 and n is going to infinity. So it's kind of like, again, like an indeterminate form of 0 times infinity. But that can be kind of arranged so that it remains a constant. So the idea is like you just assume for like the purposes of the derivation that p times n equals lambda, and that equals a fixed number. Is that okay? And I'll give you like a physical example in a moment that could be like useful to have. Well, I mean, maybe before giving you like the derivation of this formula, let me give you like a physical situation where this could appear, which is good to have. So you kind of think in practice, like you have a large container, or you have some container of volume V, and then you have n particles inside that container. Okay, so kind of like on that, like, you know, there's kind of like okay, these letters are going to all look the same in a second. So this will be, hopefully you won't get because rho is usually the name for densities. So rho would be, you take as n over v. That's kind of like a density, right? That would be kind of the particles per unit volume. Okay, and then imagine that you choose like a very small region inside this container, right? So this is like a small region inside the container. Okay, so if you don't know anything about this situation, you would like to say that the probability that a particle, I mean, if you don't know anything else, what would you say is the probability that one of the particles will be inside this region? I mean, I don't know if this would make sense, but I'll let you give it a shot. So. Any ideas? Well, you would like to say it's kind of the volume is kind of like the ratio between the volumes. And actually, we'll do that maybe Friday or Monday when we talk about continuous probability. But if you just, I mean, if you don't know anything else, like the easiest probability to assign to this is like the ratio of the volumes. That makes sense, because if you had chosen this volume to be the entire container, then the probability would be 1 for the particle to be there. Okay. And so, yeah, in this case, if you define, let me see what, oh, let me put this like with lowercase n. Yeah. I think just to use the same notation as what I have there. So in this case, if you take n times p, what would be n times p? N times p would be the following. N times P would be N times V over V. Okay, but and N over V is kind of this density rho. Okay, so it's like the density times this small volume, and that's what you would be assuming a constant. Okay, so this is what would correspond to what I'm. This would be the product, and this product N times P would be what I'm calling Pn before, and that's what I'm taking to be constant. So here it's kind of like I'm saying that the density times the small volume is being held constant, which makes sense. Like if you think like there are millions of particles inside the gas, like the density is kind of almost like approximately constant in the container, and then if you choose like a small region inside of it, then yeah, it does make sense. These two numbers would kind of be a constant factor. So it's kind of like in that sort of situation where this approximation will be used. I mean, there are other applications of some random variable that I'll give you later, but I'll like once I give you the derivation, I'll tell you how this is being applied in this case. But it would be kind of applied to find the probability of finding like a certain number of particles inside that region of the container. Okay, so I mean, just that as an aside, I just wanted to kind of tell you that this can appear in reasonable situations. It's not completely arbitrary. But so just to go back to what I was saying, I'm going to take P times N to be lambda to be a constant. So let's just rewrite what that allows you to write P as lambda over N. Okay, so in every place where P appears in the formula for the probabilities in the binomial expression, I would just replace that with lambda over N. And so that will make that will have the advantage of making the formula just depend on the on a single variable, which is N. So let me rewrite this in terms of N and lambda. So N factorial over I factorial, N minus I factorial, that's fine. P now becomes lambda over N to the I. And this one becomes 1 minus lambda over N to the N minus I. Okay, so again, like the only advantage now is that we're kind of going to find this limit, but now lambda is a constant, so all of this in this expression just depends on N. So that's the good thing. So now we're going to take the limit as N goes to infinity of this expression, okay? So let me see how can I rewrite it so that it makes sense what's going to happen now. Okay, I'll put it this way. Yeah, there are a couple of things that one needs to do here. Let me see if I can write it like this. Okay, yeah, I'll write it in this way. So I'll isolate it like this. I'll put it like this first. And I'm going to break this into, let's see. Okay, yeah, let me use a different color here. Okay, now this is ready to go. So, is that making sense? So let me just explain what I did. So these, I kept this together, which is the green one. I isolated this one over I factorial. I'm doing nothing here. I guess I just like raise each power individually to the power I. Then I broke this expression as a product of, you know, I use like the exponent rule, right? So it's like if you multiply them back together, you get this thing. Is that okay? Is that making sense? How I got each factor here. So now the idea is that each of these individually is easier to analyze. So what's, for example, okay, let's start with the most easy one, which is this one. What happens as n goes to infinity for this term? So remember now, if you take n goes to infinity, right? Lambda is fixed. I'm assuming lambda is a constant. I is fixed. I'm doing this for every I. So I is a constant. So the only thing that's varying here is like n. So you get like, I mean, as n goes to infinity, this goes to 0, right? So this gives you 1 to the negative I, and that's just 1. So this actually just goes to 1. Is that making sense? What happens as n goes to infinity here? What do you think you get? What do you get here? Let's see. Yeah. Yeah. Oh, sorry. Someone was going to say something, or
Yeah, I was just gonna say something. I remember because this one reminded me of like the limit that defines E. So I was
right?
just
Yeah.
guessing, but I double checked. It's gonna be like E to the negative lambda.
Yeah. You can do, like, if you forget about this, you can do L'Hopital's rule, because but yeah, it is kind of like, I mean, obviously one definition of the exponential number is through this limit. So it's kind of, it could be circular depending on how you define the exponential. But yeah, it is literally e to the minus lambda. Good. So that's e to the negative lambda. Okay. So we have we have e to the minus lambda, and then we just have to see what we're going to do with this stuff. Lambda to the I is fixed, so that doesn't need to be touched. This doesn't need to be touched because I factorial is also fixed because I'm fixing I. So let's just analyze what n factorial over n minus I times 1 over n to the I equals. Okay, so here is more convenient. I mean, there are different ways to say this, but it's more convenient to remember that this just means like this would be n times n minus 1 times n minus 2, blah, 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 right? Until what? N minus I plus 1, because after that, you will get n minus 1 factorial, so this will cancel. So I'm just basically writing this as a product of, well, like, I guess the n minus 1 first number, n minus 1 first numbers or something like that, okay? So you get that, and you're multiplying this by 1 over n to the I. Yeah, so here's just like a thing about counting how many factors you have. You have 1, 2, 3. Okay, so the last one, I mean, you can, it's better to write it as, I guess, I think it looks better this way. So you have 1, 2, 3, up to I factors. So here they're really I factors. And so this is nice because if n is going to infinity, if n is going to infinity, then imagine that n is like 10 trillion or 4 trillion. Subtracting 1 from 1 trillion is nothing, or subtracting I minus 1 from 1 trillion is nothing. Like n is going to infinity. So you just get n to the I, roughly, okay, in the limit, times 1 over n to the I. So these two cancel one another. And you just get 1. Okay, so they just get 1. So just to summarize, let me copy this back again here. So what I'm saying is that we just found that this part goes to 1 as well. So that means that the probability that x equals I in the limit as n goes to infinity, and again, Pn is like a constant, is giving you 1 over I factorial times lambda to the I times e to the negative lambda. And that's the Poisson random variable. So let me write that down as a definition. With parameter with constant lambda. Is a random variable x with probabilities, which has probabilities the following. Okay. Oops. Is that making sense? So this is it's a random variable that can take a value 0, 1, 2, 3, etc. Here let me write that below here. Here I 0, 1, 2, 3, 4, blah 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 blah, etc. Well, infinity is not allowed, but you know what I mean. Any integer, any positive integer. Okay. So, well, let me stop first here to see if there are any questions up to this point.
In this problem, does I represent like the number of successes? I wasn't exactly.
Yeah, it's kind of like it would be still kind of like the number of successes. Yeah. In this case, like if you go back to the gas example, in this case, so okay, just to go back to the gas example. Going back to the gas example, where I said that lambda was what? Lambda was rho times v. Rho times v. Rho, I mean, it's a. I'm trying to make this rho clearly different from the letter P of probability, right? That we use in probability. So here the probability would be that x equals I is would be rho v to the I e to the minus rho v divided by a factorial. And this is a probability, and here a success is interpreted as having a particle inside this small region in the container, right? Because that's kind of what P was, like the probability for a particle to be in the region, in the small region that you chose. So this is kind of like the probability of having I particles inside the small container. So this is like the probability of having I particles in the small region of the container, in the region V, in the region with volume V inside the container.
Okay, yeah, that makes it a lot more concrete. That makes sense.
Yeah, and so of course, like one of the things that this is saying is like then you can start asking how realistic this is, because if you look at it, this probability only depends on the volume of the container, right? And so that is more or less because we assume that the density was homogeneous across the container. I mean, if you had like a huge container, maybe you say, well, maybe you expect maybe more particles towards sea level than above. I mean, like the atmosphere, for example, if you talk about the atmosphere as a huge container, the density across the atmosphere is not constant, right? But if you have like a container, like a bottle, like a can, it is not such a bad assumption, to think that maybe the density is uniform. At least when it's in what people call in thermodynamics equilibrium. So there's like this notion of equilibrium, which is kind of where thermodynamics works best. And so it is kind of saying that the probability only depends on the volume of the container, more or less. But it's kind of giving you like a very specific formula, which is nice. But yeah, because again, here like a success is being interpreted as like having the particle inside the small piece of the container. In other contexts, like, I mean, but this is used for bus arrival times. Like this is used like, for like the number of wrong telephone numbers that are dialed on a given day. I mean, it is surprisingly versatile, this Poisson distribution. So there are a bunch of situations where it can be interpreted like the condition is like I mean, the idea of using this approximation is whenever you have these binomial these Bernoulli experiments where the chance of success is really, really small, and you're doing a huge number of these experiments. And then once that happens, you can approximate the Bernoulli distribution, the binomial distribution with this probability function. Okay. In fact, before going on, maybe I can show you like a nice animation of how these look, just to put things, make them more concrete. So I don't know if you ever had to, I mean, probably everyone is familiarized with Wolfram alpha, but Wolfram also has like a analogous thing, which is called Wolfram's demonstrations project. So if you click here, I think I just did it a couple of minutes ago to check that there was a nice animation you could download. So you can enter binomial distribution. Okay, and once you click on it, let's see, I think there's one that is comparing the binomial distribution to the Poisson random variable. So I think I downloaded it here. Let me see if I can open it. I think this one. Here it is. So yeah, you can download it for free, and then you put it on the Wolfram player. And so this is kind of comparing. It's kind of it's nice also because it gives you like an explanation. So in this model, it's like the number of cats, right, when they have probability P. And so here, like the number of tosses is going to infinity, and the probability of cats is adjusted to keep the expected number of heads constant. Okay, and so like here you can see like you can choose like a sample size. Let's see, like 30, and you can see the lambda. The value for lambda, you see like how the probability distributions agree. like the important thing of these examples also is kind of just to see that, you're kind of saying as n goes to infinity, but in practice already for a reasonable number of n, I mean, here we're choosing n equals 54. You see, it's already like a huge, very good agreement. So there's like this difference between like the mathematical ideal of taking a limit goes to infinity, and then you might think, well, maybe I have to wait like forever to actually use it. But there are many situations where like the approximation is already pretty good. So I'm just like, so I'm just saying, like, depending on how much error and things you're willing to tolerate, like, this approximation can be very well justified. And you see, like, also depending on the values for lambda, like the agreements change. The other thing that you start seeing in this binomial distribution is like this famous bell curve that kind of starts taking shape, which probably is what almost everyone recognizes, even if they never took probability theory, right? So we'll talk about that later on once we move to continuous probability, because there's another way to take a limit for a binomial distribution to get the bell curve. And that's also related to the central limit theorem and one of the other important results in probability. But I just thought that it was kind of nice to see that, like many times, like these approximations are useful, not like when n equals 10 trillion, like you can use them many, depending on how much error you're willing to tolerate and other things, this can be used way earlier. And the book, again, probably I'll try to find some examples for us to do on Friday about this, but the book has like many good examples about this to see how this can be used. Now, the thing that I did want to at least go over, because we did this limit, right? We took this limit. So when you take the limit, it's kind of not so clear, like that these probabilities behave in the way that you would like them to behave. I mean, these are just some numbers that we took with some limit procedure, right? So you have to be careful with these numbers. At least, obviously, they are like negative. They are non-negative. It's clear that they're positive quantities. But something that you do want to see is that they add up to 1, because that kind of makes, like, that's kind of what you expect of the probability for different outcomes, right? That they should always add up to 1. So what if let's try to do that quickly, right? What is the sum? So again, this is kind of like the probability for the outcome. So you would like to check what the sum from equals 0 to infinity is in this situation. But because again, that's kind of like the probability that something happens. So this is like in the case of the container, it's kind of like the probability of finding 0 particles inside that small region of the container, or finding 1 particle inside that small region, or finding 2, or finding 3, or finding 4, or finding 5, up to infinity, right? So it's kind of like you would expect that should add up to 1, because something had to occur, right? There must be like a number inside that container. So if you look, this is an easier one, because you can just pull out the e to the minus lambda from the series. And what do you get inside? You get the Taylor series for like the exponential, right? This is precisely the definition of the Taylor series. This is e to the lambda, right? This is a Taylor series for the exponential. So you get e to the minus lambda times e to the lambda, which is just 1. Is that making sense? So they do add up to 1, as you would expect. And the other thing that is useful to see is like the expected value, or the average. Is also nice to see in this case concretely. So what's the average here, or the expected value? It would be the sum from I equals 0 to infinity of I times the probability that x equals I. And so that is the sum from I equals 0 to infinity of I times lambda to the I factorial over e to the minus lambda. again, you can pull out this e to the minus lambda outside if you want. Let's see if that's useful to do. I guess so. Yes. Okay, and then let's see. Does the trick still continue to work? Let me see, because I should have computed this before.
Can we do it maybe like with just like some factor of like lambda to the I? I'm thinking.
Oh, right. You can take. I mean, the expected value should be lambda. So at some point, I do need like right. I can multiply and divide by lambda. So let's see. So now it's lambda to the I minus 1, like I factorial, right? If you just,
You can expand the factorial.
Right. This is fine, and then yeah, this is like the derivative with respect to lambda of lambda to the I over I factorial, right? Like this sounds fine. And then you can, again, you take out the lambda outside. Lambda to the I over I factorial. Okay, and then this is, yes, this is, oh, I really like this trick. It's one of my favorite ones. The derivative of the exponential is itself. And you should get lambda. And that's right. That's what's supposed to happen. So yeah, this is a fun, useful trick. So in any case, like the expected value for the Poisson random variable is lambda. So that's another reason why this lambda parameter is useful for the Poisson random variable. Lambda is the expected. Okay. Is that making sense? So far so good. Questions about this?
So I just have a question.
Mhm.
If the binomial is, if the Poisson is an expectation of the binomial, why don't we just use the Poisson all the time? Like, why use binomial?
Okay, so it's just that okay. The thing is like the Poisson, the Poisson kind of arose in the limit. Okay, it had two requirements. You have to do the trials many times, right? Because you're taking n to infinity, correct? So I mean, this, like, right? If you're doing 100 experiments or 1,000 experiments or 100,000 experiments, this Poisson distribution gets better and better. But this may disagree a little bit more with, for 5 or 10 experiments. You know what I mean? And the other condition is that you do require the, when you were taking this limit, implicitly it kind of has to work when the product of the probability, I mean, it has also this requirement that the probability is going to 0 in a way in which the n is in the way that p times n kind of is kept constant. So it does need you to kind of, it is a better approximation when the probability is kind of small in a sense. So it's not that you can, I mean, sometimes like in many situations, it's true, this will work very well. But especially for low values, for low numbers, it's not like a perfect match. And so kind of like the binomial distribution in that sense is more primitive or like more fundamental than the Poisson distribution. It's just that the problem with the binomial distribution is that in practice, like all these coefficients like that appear in the formula can be harder to compute, and in fact it's just easier to work with the exponential. But it's not that it's a perfect approximation. It does have some hypotheses like that n has to be large and things like that, so it can fail like it cannot be as good when n is small, for example, among other things. So that's more. That's why you cannot always use it. Like usually, the way in which it's used is like, yeah, you're given like a probability value that's like small and things of that sort, and then it's really large. But it's not something that, I mean, it's not that you should always try to replace the Poisson. I mean, I'll come up with, on Friday I'll do an example where you can see the difference between the two, like in terms of like the computations for the probabilities. But yeah, it's not like, no, I mean, we can try it, I suppose. Like, let's see. Here's like an example, but let me do small numbers so that you see that like the smallness kind of makes a difference. So, let's do it with n equals 3. So I think because with n equals 3, okay, yeah, let's do the n equals 3 case, because n equals 3 I already had computed before last time. So if you remember n equals 3, we had all this probability. This is the advantage of copy pasting on the iPad, that you can just copy paste all these numbers. Right, when n equals 3, we had actually computed the copy paste. When n equals 3 for the binomial one, these are the numbers that we had obtained, right? But then if you look at for the Poisson one, right? So the Poisson one, right? You see, like the thing about the Poisson one is that it also doesn't depend on the. If you put here the Poisson one, lambda, remember lambda was what was lambda? N times p, right? So lambda was n times p. If you take n to be 3, you get 3p. So here you put like, okay, let's put it like lambda equals, if you put so here's now, so this is with binomial. So this was binomial. And this is for the Poisson one. So for the Poisson one, with I equals 0, I never said it, but 0 factorial is defined to be 1, is a convenient convention. So you get 1, 1, e to the, so here you get, with I equals 0 you just get e to the negative 3p, right? For lambda, for x equals 1, you get 1 factorial is 1, so you get lambda e to the negative 3p. Here you get, for x equals 2, you get, you get lambda squared divided by 2 factorial, which is 2 e to the minus 3p. And with x equals 3, you get lambda cubed divided by 6, which is, that's what 3 factorial is, e to the minus 3p. And then you would have to check, I mean, you could just, once you have that, you can just put it on, you can start giving values for p and q to compare how much they differ. But you see, like, it is like, the claim is kind of that this will get better as n becomes larger and things of that sort, but you wouldn't expect like a very good agreement, especially for the low values for n and or lambda. Is that making sense? So yeah, that's kind of that's why it's not always that you can use a Poisson approximation. I suppose, yeah, like usually there's a hint in the problem. If they want you to use a Poisson approximation, there's like a hint in the problem that you're doing like a large number of you have either a large number of something, and so. But yeah, it's kind of like fun to see. I guess it's, yeah, useful to see this convenient. Yeah, I guess tomorrow, no, tomorrow, on Friday, I'll try to do some more other examples so that you can see this, how in practice it differs. Okay, yeah, so maybe just to, let's see, should I talk about, oh, let's go back to, I don't know if you had thought, had a chance to think about the game that I had mentioned to you last time at the end of class. So if you need a reminder, if you need a reminder, I had like 4 boxes, right? I have 4 boxes and I put like a ball inside one of the boxes, right? So maybe there's like a ball hidden in one of the boxes. So like the game was, how many questions do you need to ask? How many binary questions, right? Like, so the answer can only be yes or no. So here's the game. How many questions, how many binary questions do you need to ask? In order to locate the box in which the ball is located. In order to know in order to know the box in which in which the ball is located. Oh my god. So what was the number of questions that you need? Anyone thought about it?
I think I had somewhat of an answer last time, but I'm
Yeah,
not sure
right.
if that
So
method would work.
so how many, right? How many, if with your method, how many questions would you need?
Would it be like log base 2 of like n, given like n boxes?
Yes,
Not sure.
it's related to that, but we should start with 4 because it's more concrete, right? So in your case,
Okay.
you're saying I mean, it's actually, yeah, it is. That's the answer, but it's not so clear, right? So at this moment, but yeah, it is in this case. Like that would be 2 questions, right? That's what you're saying in this particular case because 4 is 2 squared, correct? So what you're saying with your strategy, I mean, which I think is what you mentioned last time about the binary search, right?
Mhm.
With like, yeah, the claim would be kind of like the optimal strategy. Here's like the optimal strategy. It would, I'm just looking for something. Give me a second. I don't know what happened here. Okay, so the optimal strategy would be to, you could ask first, like, you could imagine dividing, like, making questions so the probability is cut in half or like the options are kind of cut in half in terms of probability, right? So since a particle is equally likely to be in either box, right? There's a 25% chance that it will be in either one of them. So the probability is 2 boxes. A group of 2 boxes carries 50% probability, right? So you could just ask, like, as the first question, right? So question 1 would be: is the ball in box 1, 2? 1 or 2, right? So that has a yes or no answer, right? If it says yes, then you know that you only have to look in these 2. And if it says no, you also only have to look in these 2, right? So once you know that answer, right? If it has said yes, then you only have to ask, is it in box 1, right? Like, for example, if like let's do it like a tree. I guess like that's also why it's called like that, right? So if yes, you could just ask, is it in 1, right? And if no, then you could ask, so that would be question 2, right? And if you got a no, you could ask, is it like in box 3, right? And if if you are told that it's yes in box 3, you want it at the second time. If it tell you that it's no in box 3, you already know the answer, because you know that by this, like, you know, there's no other, you don't have to ask another question. Then you would know automatically that it's in box 4, right? Because you had already killed these 2 possibilities. So in this way of asking the question, right, you always only need two questions. Is that making sense? So here you do win in 2 steps, and then like by get you maybe let me put it like for 8 first, right? So for 8 boxes, one, 2, 3, 4, 5, 6, 7, 8. For 8 boxes, right? How many questions would we need? Well, first you could ask, like, for example, as your first question, is it in the first 4 boxes, right? If the answer is yes, you could ask, is then in the first 2 boxes, and if the answer to that were yes, like, you could just ask, is in box 1. So, and like, if you know, so it is like, you know, you're always cutting like from first like 50% chances, like, and then 25 and so on. So you're always cutting kind of like in half the number of options remaining. So in this case, like, you know, you go from 8 possibilities to 4, and then from 4 to 2, and then you can go from 2 to 1. So in this case, you only need 3 questions. Does that make any sense? In this case. So in general, if the number of boxes is 2 to the n, you actually only need n questions to ask. Is that reasonable? So in general. Okay. Is that okay? So far, so good. Now, here's another thing. Okay, so these can, so for the case of 4 boxes, I'm just saying you could have done this in 4 questions. Sorry, in 2 questions, right? But let's go back to that case and. So let's go to that case and let's do like a different strategy, right? So let's here's like a different strategy. Well, you could ask in this different strategy, you kind of like, you can just think of it as a like left to right strategy. So you just ask in question 1, is it in box 1, right? So you start with the leftmost box, right? So that has a yes or no answer, right? So if yes, you won, right? So this one is interesting because you in this like if you ask the questions this way, right, you never win on the first chance, right? For example, for 4 boxes, you can only win. You can only get the ball, the location on the second time, right? You can never win the first time. And here, if you ask the questions in this way with 8 boxes, you can only know for sure on the 3rd question, right? And with n boxes, you can only know for sure on the nth question. So you can never know here for sure until you have done the n question. So you can never win before n. But if you do like the left to right strategy, right, you could just get lucky, right? You could just get lucky and and you just find, and it just happens to that the ball was in box 1, and then you won the first time, right? So if you get yes, you win, or you win, right? You got the answer, the success. You can think about it as a success. If no, then you move to the next one, to the right. So you move one step to the right, and then you ask the same one for question 2, right? Ask the same for box 2, right? So now I'm in box 2. If the ball is in box 2, I'm happy. If it's not, then I have to move to the third box and ask the same. Is that making sense? So okay, so we know that we could win here on the first time that you ask the question, or even the second time. How many questions are the max number of questions that you need to ask in this strategy? What's the maximum? How many questions do you need to ask here?
Like 4, I guess 2 to the end.
Well, you have to be careful, because actually, if you are like on the third time, right? Imagine you got to this location.
Yeah.
If I get a yes, good. If I get a no, then there's only one chance. There was only one case remaining, so I already also automatically know the answer, right?
Yeah.
So it actually only needs 3. Like, you can make this a little bit more realistic, like better. Like if you had like you can do it like with 8 boxes first if you prefer, right? But again, it's kind of like, yeah, you could win on the first time, you could win on the second time, blah 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 blah. But if you keep losing, then once you get to the 7th box, right? If it's a yes, you win, and if it's a no, you also know for sure that it has to be in the last one, right? So with this left to right strategy, you actually need at most n-1 questions. Is that making sense? So with this strategy, you need at most n-1 questions. Is that okay so far, so good with everyone? But now here's like an interesting question. Like, you could say, well, why is a first strategy better, right? Because like with this one, you can win like earlier, right? With this strategy, you could win a bit earlier. So it's not so clear that which one is better. And the only way to actually find out which one is better is to actually compute some averages. So we actually have to ask for the average number of questions that you use in this strategy, because sometimes you win on the first time, sometimes you win on the second time, sometimes you win on the 5th time. So it's not fair to kind of like, you cannot just compare those numbers. You have to compare the average number of questions in this strategy versus the other strategy. In the other strategy, oh, sorry, like the boxes I was choosing, it's n-1 questions if there are n boxes, but here, like, it was really 2 to the n minus. This could look a little bit weird because I was calling the number of boxes 2 to the n. So let's just keep it to 2 to the n boxes. Right, so now it looks a lot a difference, because right, like it's just the same number of boxes minus 1 versus the other strategy where the number of questions was always n, was basically the exponent, right? When you write the number of boxes as a power of 2. So what you have to do is actually compute the expected values. So let's just define a random variable that's going to go from x to 2 to the n-1, which is like the number of questions needed. So x is going to be the number of questions needed to find the box, to find the ball, to determine where the ball is located. So I'm almost going to finish with, I'm almost done. So what's the probability? Let's just work out some cases first. What's the probability that x equals 1? What's the probability that you get the right answer the first time? Again, remember there are 2 to the n boxes.
Just like 1/2 to the n.
Yeah, because like if everything is distributed randomly, like you have 1/2 to the n chances for the box to be there. So yes, it's 1/2 to the n. What's the probability that x equals 2? That on the second question, I mean, assuming that like again, like you would only get to the second question if the other one wasn't there, but like it's kind of like asking again, what are the chances for the ball to be located on the second box, right? And that's also 2 to the 1/2 to the n. Okay, and then you kind of keep going. Now you get to the second to last ball of question, right? And that still continues to be 1/2 to the n. But once you get to the last question, right? Remember that the last question is actually going to give you an answer for the remaining 2 boxes, right? The third question would give you the answer for the third and fourth boxes. So actually the last question gives you kind of twice the information, like has twice the probability associated to it because it represents 2 boxes. So the probability for x to be 2 to the n minus 1 is 2/2 to the n. Okay, so what's the expected value? Or what's the average? So the average value here is just it's just this. And so that's just right. This is the probability sum from I equals I to 2 to the n minus 2 of I times 1/2 to the n plus the last one, which has like a slightly different value. Okay, so that gives you the sum from I equals 1 to 2 to the n minus 2 of 2 to the n of I/2 to the n plus, okay, this, I mean, you can write it as 2 to the n over 1/2 to the n minus 1. And so this is kind of like the sum of the, like, I mean, I guess I should have, it's kind of better, it's probably better if you call, it's maybe better looking if you call m2 to the n, just to say the number of boxes. Yeah, otherwise it looks a little bit too ugly. So you can just say this is the sum from 1 to m minus 2 of I over m. Yeah, that looks a lot nicer. Plus m minus 1 over, so let me put it like this, 2m minus 1 over m. Okay, and then, yeah, here you're just adding up together the first m minus 2 integers. And so that's like what? And minus 2 times m minus 1 over m plus 2m minus 1 over m. Okay, so you can factorize an m minus 1, so over m. So you get m minus 2 plus 2. Wait, am I doing this? Yeah, let me check if I'm not doing anything correctly here. Just give me a second. Oh, I forgot a 2 here. That explains it. It's like, yeah, like the sum for the n first numbers is n times n plus 1 over 2. So that's like, that makes that fixes it. Well, I mean, the precise values are not too important. The point that I'm trying to say is that the average number of questions, like the only thing that matters of this calculation, like, wait, here I wrote it, is that like this kind of, you know, this grows linearly with m, right? It's if m is 2, if you're asking a lot of questions, I mean, this is kind of like m minus 1 and m plus 2 are more or less essentially the same. So this is kind of like n squared over m. So this is roughly like m. Oh, m over 2, sorry. Oops, killing me. So I'm just saying it's kind of like the number of questions in this strategy grows linearly with the number of boxes. So the number of questions here grows linearly with the number of boxes, with the number of boxes on average. But in the other strategy, the number of questions was grew logarithmically, because in the other strategy, where m is 2 to the n, we needed n, which is natural log of 2m questions. So that grows logarithmically. And if you have ever seen the graph of natural log of x versus x, for example, you can see that there, even though both are going to infinity and as x approaches infinity, you can tell that there's like a very big difference in how those values grow. So that's kind of like all these questions about finding like and you know, logarithmic growth is way smaller than like a linear growth, because logarithmic growth is kind of like the inverse of the exponential growth. So it's a lot, it grows a lot slower. So I'm just saying that at least when you compare these two strategies, one has logarithmic growth with the number of questions and the other has linear growth. So it is, at least in that case, versus those two, kind of clear that the one is better than the other. What happens, yeah, I'm not sure like how many details I should give about this, but what happens is that, yeah, this first strategy is kind of related to the number of bits needed if you were to describe like the you know, like the random variable. So that's kind of called the entropy of the random variable. But again, I'm not sure. I mean, maybe if we have more extra time, I'll tell you more about that. But it's kind of it's a nice concept. But yeah, I guess I think for now, I just wanted to give you this example because this is a fun game where you can see how you can use random variables and expected values to compare certain things. But yeah, but again, this thing about the entropy is fun, but if we have time, I may tell you a bit more about it later on. But yeah, for now, on Friday, what we'll do is I'll probably try to do a couple of examples with these random variables, but we may start at the continuous case. So it will, and we also have to talk about the variance. But yeah, I thought at least I wanted to give this example because it's a fun example to keep in mind. But yeah, I think it's a good place to end because it's almost 8 p.m. also. So maybe we should end here now. So I'll see you on Friday if that's
All right. Have a good one, Professor.
okay. You too. Bye.
Thank you, Professor.
Bye.
Thank you, Professor. See you.
Bye.
Have a good day.
You too.